Okay, this shouldn't be too long of a video. I think you're going to find this to be pretty easy. It's kind of just a combining of some of the things that we've already learned. So this is from section 17.5, factors affecting solubility. And there are a few things that will affect how well an ionic compound will dissolve in a solution. There are some things you can do with something that doesn't dissolve very well in order to help it to dissolve. So, or actually there are some things you can do to it that will cause it to not dissolve as much even. So the first thing we need to talk about is the common ion effect. And we've already kind of talked about the common ion effect right before we talked about buffer solutions in this chapter. But if you've already got an ion in a solution, that's going to be one of the ions in the solid that dissolves, it will dissolve less. Okay? So an example of that, we've got this BaSO4 solid dissociating a little bit into Ba2 plus and SO4 2 minus. Okay? Let's say, for instance, that we put the BaSO4 into a solution that already has some BaCl2 in it. Okay, so we and when I say BaCl2, what I really mean is it's got Ba2 plus and Cl minus in it. So it's already got some of the Ba2 plus, right? So because we have more of this, you can kind of think about it in terms of Le Chatelier. And think about a shift of equilibrium. Because we have more of the Ba2 plus, that's going to push the equilibrium back this direction and make it less soluble. Okay, so that there would be more of the BaSO4 just sitting at the bottom there, and not as much of the Ba2 plus and SO4 2 minus would show up. So that's kind of conceptually the common ion effect. Now, they have specifically said, excuse me, they've specifically said in the AP curriculum, there's an exclusion statement that says that you don't really have to do any calculations that are related to this. Now, I'm going to show you one just because I think it's always good to look at the calculation at least, because I think calculations, sometimes people's brains work that way, and so it's going to be easier for you to think about it in terms of numbers than it is just conceptually. So I'm going to show it to you, but you're not going to be responsible for actually performing a calculation like this on my test or on the AP exam. They specifically have said that. So, well, I guess I have to do it right here. So let me erase this stuff that I've already got here, and then I'll change my pen color and I'll just write over this slide, which hopefully is legible. Okay, so the sample exercise in the book that goes along with this is calculate the molar solubility in of CaF2 in a solution that is 0.010 molar in CaNO32. And then they have a second example there. We'll just go over the first one. Okay, so first thing that you would want to do on this one probably is write the relevant equation for the solubility of CaF2. Okay, so remember on these, we usually write the equation this way. You put the solid on the left side, you put it in equilibrium with its ions, Ca2 plus 2F minus on this one. Okay, and so here's the change on this one, where what we have been doing is putting zeros. So you get your ICE here. We have been putting zeros for the Ca2 plus and the F minus. On this one, there is going to be a zero for the F minus initially. Okay, but because the solution already has 0.010 molar CaNO32 in it, it has 0.010 molar Ca2 plus already in the solution before we dump in the CaF2. So that's your initial amount. Okay. So then we don't know anything else other than the KSP, which actually doesn't give it to you at the beginning of the problem, but they give it to you in the solution, and you could also look it up in the appendix. I think it says it's in Appendix D. So you've got the KSP for this reaction, and you've got your initial concentration of Ca2 plus and F minus, and that's all we have. So this is one of those plus X problems. Okay, so this one is going to increase by plus X. This one's going to increase by plus 2X. So then what we end up with is 2X and 0.010 plus X. Alright, now this gets a little tricky because when we set up our KSP expression here, our KSP for this one is 3.9 times 10 to the negative 11th is equal to, and notice what we're going to have here, because we have to square the F term, even if we didn't have to square the F term, when we multiply these two together, the 0.010 plus X times the 2X squared, I'll just write out what that's supposed to look like. 0.010 plus X times 2X squared. We're going to get a nasty, not just a quadratic here, we're going to get a an x to the 4th power. So that's just, we don't want to have to deal with that. So what we can do here is the simplifying assumption again. Okay, notice that the solubility of CaF2 is the KSP is 3.9 times 10 to the negative 11th. Okay, what that tells me is the amount of Ca2 plus that's going to come from the dissolving of CaF2 is incredibly small compared to the 0.010 molar Ca2 plus that's already in the solution. Alright, so then we'll make our simplifying assumption here, and we'll say that 0.010 plus X is essentially the same thing as 0.010. Okay? I'll just change that to 4x cubed, or 4x squared, sorry, squared. Okay. So now we can solve this thing just like normal. Solve for your x, solve for your solubility, and once you do that, you should end up with an x value of 3.1 times 10 to the negative 5th. Okay, and that x value is our solubility for this. Okay, so what you're going to notice here is that if we were just doing this normally without the 0.010 in there, you'd actually end up with a higher value for the solubility of the CaF2 than you end up with here. Because if you just did it without the 0.010 or any of that in there, what you'd end up with is 4x cubed, right? So we'd end up taking the cube root of this 3.9 times 10 to the negative 11th, which is actually going to make it a quite a bit higher number. Okay, and I don't have a calculator down here with me, so I can't calculate exactly what that number would be. But basically, what you would end up with on a normal problem like this, without the 0.010 in there to begin with, is that you'd end up with 3.9 times 10 to the negative 11th is equal to 4x cubed. Okay. So you divide both sides by 4, and then take the cube root of both sides, and then that's going to give you your solubility that it typically has, and that number is going to be bigger than this number. Okay, which again, just in calculation form, proves what we talked about with Le Chatelier here, that the equilibrium shifts to the left towards the reactant side if you already have some of the common ion in there. Okay, so in other words, the CaF2 would be less soluble when you already have some CaNO3 in the solution than it would be if it was just you were dumping it into distilled water. Okay, and then you can also look at B and you can kind of predict what's going to happen there, because that has NaF in it, and the NaF obviously has the common ion of the F minus. Now, you can look in the book and you can kind of see that because of the 1 to 2 stoichiometry that's going on here, it's even more, it affects the solution even more. If you have F- ions in there, it's going to reduce the solubility of the CaF2 even more. Okay, and I think it ends up being 3.9 times 10 to the negative 7th is what it says here. Okay, so hopefully that makes sense. Another factor that can affect solubility is the pH. Okay, and then just a couple general rules here. Now you should read more about this in the book than what is here. But if a substance has a basic anion, it's going to be more soluble in an acidic solution. So you can kind of think about this again in terms of Le Chatelier. So if you've got a the one they have in the book is magnesium hydroxide. So, and I'm going to write this up here because it's a little bit easier to read, I think. So our equilibrium for magnesium hydroxide would be Mg, sorry, that's a G, Mg2 plus plus 2 OH minus. Okay? And the way you can think about this one, again, is still Le Chatelier. If we put this magnesium hydroxide that's doing this equilibrium into an acidic solution, then what we have there is a bunch of H plus running around. Really H3O plus, but we can think of it as H plus here. Well, the H plus is going to react with the OH minus. So the OH minus is essentially going to be taken out of the solution, and it's going to form just water. The OH minus reacting with the H plus. So then, if you're taking away a product, again, based on Le Chatelier, that's going to shift the equilibrium to the right, or towards the product side, which means that the MgOH2 is more soluble. Okay, so you put something that has a basic anion into an acid, and this is going to happen. Okay, it's going to increase the solubility. And so that's what they're saying with this first one here. If a substance has a basic anion, it will be more soluble in an acidic solution. Now, it doesn't just have to be hydroxide. It can be any anion that's basic. So you could have something like calcium carbonate. Okay, so CaCO3 solid, again in equilibrium with Ca2 plus. Sorry, this is going to be a mess. CO3 2 minus. But same thing, the CO3 2 minus will react with H plus. So you're basically taking this CO3 2 minus out of solution, taking away a product, causes the equilibrium to shift towards the product side. So anything that has a basic anion, you put it in an acid, and this is going to happen. Okay. Substances with acidic cations are more soluble in basic solutions. An example of that, I'm trying to think of a good one here. Well, I think the one they talk about in the book maybe is aluminum hydroxide. Now, they really don't talk about the other way around. It doesn't look like in the book. They only talk about the basic ones being soluble in acidic solution, which is kind of strange. They kind of talk about it a little bit over here when they talk about on page 748 when they talk about Anfo Terrorism. Because what happens there, so you could have something like, you could think about this in terms of aluminum. So let's say you've got something like, trying to think of a good one here. I don't know, aluminum carbonate. I don't really know how soluble that is in water, honestly. But you've got your equilibrium here. You've got your aluminum 3 plus, and your CO3 2 minus. That's supposed to be a minus sign. Sorry, I'm running out of room. But let's say that you put that into a solution with hydroxide in it, so it's got some OH minus. Okay? Well, aluminum will react with the hydroxide to form aluminum hydroxide. So if that's the case, again, you're taking away one of the products, and that's going to shift the equilibrium towards the product side and make it more soluble. So same thing works if you've got an acidic cation that can react with a base. They just don't talk about that one as much until they get to the Anfo Terrorism. Okay, another factor that can affect solubility is if there's a complex ion that forms. So the example that they give here is AgCl. Okay, so you've got something like AgCl, solid, in equilibrium with Ag plus Cl minus. And again, the book presents this a little differently. I think the easiest way to think about this, let's say you put this into a solution with some concentrated ammonia. So there's a lot of ammonia in there. Usually it's got to be concentrated in order for the complex ion to really significantly form. So you dump in a bunch of the NH3 into this solution. Okay? Well, what's going to happen is this silver will form a complex with the NH3. Okay? And you can see this up here. Okay? The silver likes to form a complex with NH3. As you can see, the Kf for this reaction is very high. 1.7 times 10 to the 7th. Okay, so you dump in a bunch of NH3 and this is going to happen. Once again, you're pulling a product out of the equilibrium, so that's going to shift the equilibrium towards the product side and make this more soluble. Okay, so where AgCl would not be all that soluble in just water, if you dump a bunch of NH3, concentrated ammonia, into that solution, then the AgCl is going to pretty much completely dissolve because all the silver will complex with the NH3. Okay? Okay, and there's the example that they show there. Which, again, I kind of like my way of thinking about it and writing it a little bit better than the way they have it there, but it's basically the same concept. Okay? You also have Anfo Terrorism, and this is where I was talking about the aluminum. Okay, so examples of cations: aluminum, zinc, tin. These things can actually act as acids or bases, just depending on the situation. So, what can happen here? And they just explain this very briefly, and I don't think you're probably going to see this on the AP exam. I probably won't hit on this really on the test. If I do, it might be one conceptual question or something like that. But the idea here, and you've kind of seen this already with complex ions in the rainbow equilibrium lab that we did. But the idea is a couple of different things can happen. One thing that can happen is you've got this just aluminum in solution, okay? And so the picture that they show here initially is you've just got aluminum, and now this aluminum, because it is it can act as an acid in solution, it's going to complex with the water molecules a little bit, and it's actually going to cause that solution to be just a little bit acidic. Okay, but what can happen here if you add base to that? Then initially it can form this this complex ion right here, where instead of just being attached to water molecules having 6 water molecules surrounding it, now it's got 3 water molecules and 3 OH minus, because OH minus can be a ligand just like water can. It's actually probably a better ligand because it's negatively charged. So you dump the OH minus in there, and when you have that combination of 3 to 3, 3 water molecules and 3 hydroxide molecules around the aluminum, then you're actually going to form a solid. Okay, that's precipitates out of the solution. But if you keep adding OH minus, then it can shift back, and you end up with this complex right here, which now has 4 OH minuses and just 2 of the H2Os. And at that point, it redissolves. Okay? And so it's basically just showing that the aluminum can kind of do different things in the solution. It can kind of act as an acid and act as a base, depending on the concentration you've got in there. Okay, and so you add a little bit of base in because that aluminum was initially acting as an acid. It's going to react with the base, and precipitate. But if you add enough base, did I say that right? It's acting as an acid, reacting with the base. You add enough base, then it actually becomes basic. There we go. So over here, it becomes basic, and then it redissolves in the solution. Okay? So that's the basic idea there. The basic idea. I don't think there's anything else we need to talk about from that section. Pretty straightforward stuff. I don't think you guys are going to have too much trouble with it. Like I said, the Anfo Terrorism, that's the most complicated part of this, and I don't think that's you're going to see much of that. As long as you understand how the complex ions, the pH, and the common ions affect solubility in a conceptual way, you can explain it in terms of Le Chatelier, then you guys should be just fine. Alright, we'll see you in class tomorrow.